Okay, so 1.3, you might have noticed in this chapter, we are looking at what makes something a function, how do some functions look differently than others. Yesterday we talked about even and odd and their symmetries. Today we're talking about something called continuity and end behavior and limits. Now this is something that will prepare you if you ever take a higher level math in your future. But again, all of these things go together. It's about what a function looks like, what's it doing, all of those things. So first let's talk about continuous function. A continuous function is a function with no gaps, holes, or jumps in it. So when I think about drawing a continuous function, once you start drawing, you never have to pick up your pencil.
Are we spelling like holes like that with a W or just a?
Because I'm a dork and can't spell. How about with just an H? And you know, when I went to write it, I was like, yeah, anyway, thank you. So you never have to pick up your pencil. It's a function without gaps, jumps, or holes. So let's look at an example of a continuous function. So let's draw a few different. Okay. So one example would be a cubic function. So you see that once you start drawing it, you never have to lift your pencil. A quadratic function. Once you start drawing it, you never have to lift your pencil. A linear function. Once you start drawing it, you never have to lift your pencil ever again. So that's just a really good way to kind of think about it. So those are examples of continuous functions. If we know what a continuous function is, and then our goal is to look at, well, what is a discontinuous function? What does it mean for it to not be continuous? So that's a discontinuity. So that's going the opposite direction. An infinite discontinuity is a gap where there is a vertical asymptote. So you might say, well, what the heck's a vertical asymptote? An asymptote is a line that we can approach and get super close to, but never cross. So an asymptote is a line we can get super close to, but never cross. So what does that look like? I'm going to draw a little picture over here to kind of match that particular situation. So in infinite discontinuity, there might be a vertical line that we get super close to on the left or super close to on the right. And oftentimes they look something like that. So this gap, if I were drawing on my pencil, in order for me to get to this piece over here, I had to lift my pencil. So you had to lift your pencil. At the asymptote. Now this occurs very often in a fractional function where the denominator equals 0 is a common way that this happens. So that's your first type of discontinuity. Mathematically speaking, if you look at the spot, you usually get some number over 0. Algebraically. So remember, our algebra and our geometry have to somehow go together. And if you were to plug in, let's say this is some value A. If you were to plug in f of A, you get 4 over 0, 2 over 0, 7 over 0. You would get a number, not 0 over 0, because that's something different, but if you get just any other number but 0 over 0, it's indicating you have found a vertical asymptote. Okay, so that's our first type. The next type is a jump discontinuity. A jump usually occurs because it's a piecewise function. So the two pieces are disconnected. The two pieces are disconnected. Is that how you spell connected? I don't think it is. I think that's better. So usually this is a piecewise function. Now some piecewise functions, the pieces connect, and you don't have this issue. So in this particular case, we would have this graph where we would have one piece, then there's some kind of disconnect, and we would have a different piece. So at this value A, there is a disconnect. And so it's a jump. Okay, so that is our second type of discontinuity, or jump in the graph, or hole in the graph, or spot in the graph where something is messed up. The last one is called a removable discontinuity. Removable means there is just a hole in the graph. There's just a hole in the graph. Algebraically, that is going to show up as 0 over 0. That indicates a hole in the graph, algebraically. But what does that look like on our graph paper? Well, on the graph paper, it could just be a function where there's just some little hole they've indicated for some reason at A. So an infinite, you come across a vertical asymptote. A jump, there are just two pieces of the graph that are disconnected. I think about the fact if I have my little math bug and he's walking along, when he gets to that spot, he has to jump up to the other spot. And then removable, there's a little hole as he walks along the graph that he has to jump across. So there's some reason, bless you, that you had to pick up your pencil, that you had to somehow disconnect from the graph. So a discontinuity, think of a disconnect. Somehow pieces of the graph are not linked together. Okay. So we need to be able to recognize what they look like. We need to be able to recognize how it shows up in the algebra. Okay, so let's take a look at f of x equals x squared minus 3x minus 1. The example is asking, is there a discontinuity at 1? Is it continuous at 1? Well, the first step to check is plug it in. Okay, so if I stick 1 into our graph, I get 1 minus 3 minus 1, or I get negative 3. So that seems to indicate that there's a point there at 1, negative 3. If we were to graph it, I was trying to think if I can at least give you an accurate graph. If we were to graph it, it's a parabola, but let me see if I can get you a fairly accurate graph. Okay. Did I put that in right? X squared minus 3x minus 1. Yeah, okay. If we were to graph it, it looks something like this. Sorry, it's a little lopsided there. And as you can see, if it's at the point -1, -3, it's about right there. My math bug could walk through that point. There's no issues there. And some things to remember. This is a polynomial. Polynomials are always continuous. Now, what makes it a polynomial? So x squared minus 3x plus or minus 1 is a polynomial. If all of the powers are whole numbers, there are no fractional or x's in a denominator. X squared minus 3x minus 1, 2x plus 4, x to the 5th minus 4x plus 3. All those very nice ones are always going to be continuous. They don't have holes, they don't have gaps, they don't have anything that would mess them up. Now, in our second example, it's a piecewise function, and they're asking, is it continuous at -3, and is it continuous at 2? So see how -3 is our border value? The border may cause an issue. So this may cause an issue. 2 isn't on the border. It'll be fine. But -3 is on the border. Now, how do we check to see if it's continuous? We need to know if the pieces are connected or if the pieces are not. Well, if I plug -3 into the top, and it's not supposed to be there, but I just need to know, is it connected? So 3 times -3 minus 2. If I plug it into the top function, I get -9 minus 2, or -11. So if my math bug is walking toward -3, to the right of -3, he is at a height of -11. Now let's see what happens on the other side. So if you put in 2 minus -3, you get 2 plus 3, or 5. There is a disconnect there. On one side, our math bug will be at a height of -11. On the other side, he'll be at a height of 5. There's a disconnect. Those pieces aren't together. So it right here has a jump. So a piecewise function will usually, if it's going to have an issue because there's a jump. Now, we had practiced plugging into piecewise functions, I think, in one of the very first lessons we had done. Let's check what's happening at 2. Now, 2 is greater than -3, so it fits that top category. It's nestled way after -3. 2 is to the right of -3 by quite a bit. And so f of 2 is 6 minus 2, or 4. It's okay. It's continuous there. A piecewise function to the left of the border, that would be this one, to the left of the border of -3, every single place is continuous. It's just a line. To the right of the border of -3, it's continuous. It's just a line. It's only at that border value you have to ask yourself, do they come together? Now, if you've never tried, there is a way to actually put these into Desmos, so I want to show you how to do that. I just have to write it down before I jump this page. Okay, so let me show you how to put this into Desmos. It's going to be important as you try to check your work and you're checking to see what's happening. Okay, so if we go to Desmos, here's how you put in a piecewise function. So you type in that top one was 3x minus 2. You hopefully wrote that down. And here's how you tell it that you want it to be greater than -3. So you just do a squiggly bracket. Let's see if I can make a squiggly bracket. So you just do a squiggly bracket. Maybe I can do a squiggly bracket. Where would a squiggly bracket be? Squiggly bracket, and then you say x is greater than negative 3. And that's telling it to restrict the function to negative 3. So look, see how the line stops at negative 3? See how it says the word undefined? What that means is that you can't be equal to negative 3. That's not included. It doesn't have the little equal bar. Okay, now let's put in the other piece. Where did I write that? There it is. Okay. Our other piece, sorry, I suck at typing into Desmos, is 2 minus x. Again, we do put in our squiggly bracket, and we say in this piece, x is allowed to be less than or equal to negative 3. Then we end our little squiggly bracket. And see the pieces? See how at the top one, we're at a height of 5, which we talked about. In this one, we would be at a height of negative 11. It has a hole there, so it's not going to say it. But see how there's a definite jump. If my math bug was walking up here, if I could get it to do it. There we go. If my math bug was walking up here, he would have to physically leap down to this other piece before he could start walking again. So that's a jump. He would have to jump. And so it was named for that very reason, that the pieces are disconnected. It is not continuous at negative 3. But over here, I can never have to lift up my pencil. On the red piece, on the blue piece, I never have to lift up my pencil. Okay. So that's what it means to have a jump discontinuity. A piecewise function, we only really have to look at the border value of negative 3. What's happening? Are those pieces disconnected or connected? Okay. And then we have a possibility of having what is called a hole, or what else do they call it? A removable discontinuity. Okay. So let's plug 3 into our function, and let's algebraically look and see what's happening. Because we want to check, is it continuous at 3? Well, if you get, if you plug in 3, watch what you get. You get 6 over 0, okay? Now let's plug in negative 3. At negative 3, we get 0 over 0. Now, both of those are undefined points. So they are discontinuous at both. But they're different things happening. A number over 0, like 6 over 0, is telling us that we have found a vertical asymptote. And I'm just going to abbreviate that VA, vertical asymptote. If you see me write down VA, I mean vertical asymptote. And so that's called an infinite discontinuity. If I get 0 over 0, that is indicating that there should be a hole in the graph. That is called a removable discontinuity. Okay? So this graph, and fractional functions, rational functions like this, could have 2 types of discontinuities. They can have removable, they can have infinite. So they're kind of a unique case. And the algebra is going to kind of lead you to the answer. If you get a number over 0, where the top is something other than 0, that's telling you we found a vertical asymptote. If you get 0 over 0, we have just found a hole. Okay, so now I'm going to go back into Desmos, because you see how good I am at it. And I want to show you how each one appears. Now, to make a rational function in Desmos, the most effective way to do it is put the top in parentheses. So I'm going to put x plus 3, and then hit divided by, and then put the bottom in parentheses. So then it will clearly define what is your numerator and what is your denominator, and it won't mess anything up. Okay. So it is this one of these functions that has these two gaps. And think of our math bug walking along the function, okay? So I want to look at x equals 3. And I also want to look at x equals negative 3. Okay. First, let's look at the purple one. See the purple graph, or the purple line, I'm sorry? The purple line is an asymptote. If you're walking along the green function, you're going to get super close to it, but you can never touch it. Here, super close to it, but never touch it. That is a perfect example of a vertical asymptote. We said that 3 had one of those, okay? Now let's take a look at negative 3. I'm going to turn this line off for a minute. Watch when I walk across the graph, if it lets me. There we go. Okay, watch what happens when I hit negative 3. See what it says? See how it shows the little hole there? Sorry, it's hard to stop there. But it shows the little hole there. But if you lift your finger or your mouse at that point, it doesn't physically show it. So it's knowing that you know. So Desmos doesn't physically put the hole on there that it should. But if you go past it with your finger, it will show it, okay? So just so you know, it exists. It's an undefined point. So both of those things that we thought were happening occurred. At 3, we had a vertical asymptote. At negative 3, there was a hole. The algebra and the geometry always go together. Okay. Do we have any questions at all about this first stuff? Brand new stuff. I don't know if you've ever seen anything about the words continuity before. Did you do that in pre-calculus? Okay, so let's take a look now at our last example. And it says find the discontinuities. Okay, now it's easy to locate them, but I also want you to show me how. So just take a minute and try to draw a very rough graph of this on your paper, okay? So draw that graph on your paper. You probably have it in front. Just do your best at pinpointing the locations. Please draw this picture on your paper. Once everybody has it drawn, we're going to go from left to right and kind of pinpoint all of the issues on the graph. We're going to try to pinpoint all of the issues that are on that graph. So do a little rough sketch on your paper, draw that graph, and then we're going to talk about it. Trying to see if I can get the picture to be any littler. I guess I can. Take a second, draw it out best you can, just a little sketch, so that you can write on the sketch what's happening for those particular points. Now, luckily, we don't have to know the equation to this, because you can notice that the equation to this is would be pretty crazy, because look at all the different pieces to it. So this would be a piecewise function. Now, all the pieces seem to be, well, I don't know if they're all linear either. Anyway, okay. So what we're going to do is, at the bottom of the graph, I am just going to pinpoint when I had to do a little jump to another piece. Okay, so let's start at the left side of the graph. Here's my little math bug. He's walking along, he's walking along, he's walking along. Oh, there's a hole there. He has to jump up all the way up to here in order to keep going on the graph. So that's an x value of -3. So let's just put down here x equals -3. So that indicates that our math bug jumped at that point, okay? So now he jumped up here. So he's up at the top there. He's a-walking, he's a-walking, he's a-walking. Oh, he's walking. Everything's great, everything's great. Oh, there's a hole there. And that is an x value of -1. So let's put x equals -1. And he's leaping up to here. Boop, he jumped up here. And he's walking, and he's walking, and he's walking, and he's walking, and he's walking until he gets to an x value of 5. So let's put that as an x value of 5. At an x value of 5, he has to jump up here. Now, he can't stand there, but he can get super close. So let's put him on the other side. And he's walking, Oh, an x value of 6, he has to jump again. So let's put under here. I'm running out of room, but let's put x equals 6. And he's walking, he's walking, he's walking, he's walking. Oh, there's a problem at x equals 7. He can jump up here to get close, but he still has to jump at x equals 7. And then he's walking, and then he's walking, and he's walking, he's walking, he's walking, he's walking, he's walking. He never has to stop ever again, okay? So let's evaluate what is happening at -3, at -1, at 5, at 6, and at 7, okay? Okay, so let's talk about -3. At -3, on this left side, there is a hole. So we would say that the left side has a removable discontinuity. Okay? But on the right side, he can get close to this vertical asymptote. So on the right side, there is a vertical asymptote. Well, you can call it an infinite discontinuity. So he was walking, he was walking, he was walking. And I didn't have to lift my pencil, but I got a hole at the left side as I was walking from the left. So that at -1, here, let me change colors. I have a left removable again. And then, so that's here. And then I leaped up here. It seems to be fine. There's nothing wrong. The right is okay. Okay, because it has the closed-in point. You can keep walking. Okay. Now let's look at 5. So he's walking, he's walking, he's walking. Left side, he can walk right up to it, no hole. The left side's fine. But to get to the right side of an x value of 5, he does have to leap up here. There is a hole. So that would be the right would be removable. We could remove the problem if we stuck a cap on that hole. No, we can't. But if we could, that's the way I kind of remember that. It's kind of silly. Okay. Then he's walking, he's walking, he's walking. Oh, there's a little hole in the ground there. He has to leap across it. The hole is a perfect hole on both sides. So the left is removable. The right is removable. So we can just really say that this is considered a perfect removable discontinuity because both the left side and the right side are doing the exact same thing. There's a hole there. If he leaps across it, that's all the only problem, okay? Okay, now he's walking, he's walking, he's walking. Left side, the left of positive x equals 7, he has a hole there, so that's removable. He leaps up here. See how they skim it across that vertical asymptote. So the right side is a vertical asymptote, which is called a infinite discontinuity. Okay, so if you ever take calculus in your future, you will be playing around with these different types of discontinuities and what the formulas look like. In a calculus class, you dive in a little deeper as far as the equations. We're not going to go that route. The main thing to remember that I would say is to remember is that if you get a number over 0, it's a vertical asymptote. 0 over 0 is a hole. And if it's a piecewise function, check the border. Just know those 3 things, and then you're good to go, okay? So your homework, there's some graphs, and these are just checking 2 values. You're telling me what it is. These, same thing, 2 values. This is like the graph that we just saw. So you would just label the point and tell me what's happening on the left side and the right side of that. But I want to talk about this section here, okay? So you have 10 problems to do. Here you're sticking in -5. If it works, great. Then open up Desmos, look at the picture, and say, yeah, that point is great. It's wonderful. It's fine. There's a point in the graph there. Oh, that seems to be a jump. Oh, that seems to be a, just plug in the point, see what the algebra tells you, use Desmos to see what the graph tells you. I wouldn't expect you to graph them yourself. So that is your job for the rest of class today. I'm thinking maybe tomorrow we might just take some time to let you work on this homework, these two homeworks in class, because they're weird and I want you to be able to ask me questions. But for now, try this homework, start this homework while it's fresh in your mind, okay?